now I'm going to introduce our next speaker. So we're going to stay a little bit more on kind of the materials theme. So our next speaker is Andreas Arrieta from Purdue. So thank you very much, Andreas, for joining us. And if you want to try sharing your screen, fantastic. Thank you. And I'll hand over to you. Thank you very much for joining us. Oh, sorry, we can't hear you. I think you're muted.
Sorry.
Perfect.
Thanks for the introduction, Josie. I just want to make sure that you're seeing the correct slides.
Yes, embodying mechanical intelligence.
Yep. Cool. All right. Fantastic. So I'm going to, kind of return a little bit to the discussion from the first talk from Matej and talk about embodying mechanical intelligence from geometry and mechanical constraints. And our main motivation is, of course, related to the rise of artificial intelligence and how can we bring it in contact to the physical world. So we're very familiar with many different embodiments of intelligence in silico. For example, there was big news when AlphaZero, reinforcement learning type of embodied of intelligence, taught itself to learn to play chess and other different games in very, very small number of steps, and was able to reach to become, the best chess player that we have in the planet. And this is interesting because, of course, chess is one activity where humans practice and is related to a certain capacity, to visualize different type of outcomes, certain intelligence. And now the question is, this AlphaZero training required significant amount of power that was, close to what is needed to power 400 households in the US. And it's also, and this is only to develop this kind of capacity of playing very specific type of game. Now, if we compare the ability of AlphaZero to play chess, that is measured by what is called the ELO rating, we compare it to the best top ELO rating from a human, which was from Magnus Carlsen at 24 years old. The total energy that Magnus required to grow until 24 years was a little greater than the one that was needed to train AlphaZero. But of course, Carlsen can do many more functions, and in particular can manipulate the pieces when playing chess, so it can interact with the physical world. Now we're seeing even more impressive forms of intelligence embodied in silico, like for example ChatGPT, which can really produce very complex reasoning. One wants to see it that way, but has no exchange with the physical world yet. So then there's been significant efforts in trying to embody intelligence and try to generate systems that can learn as they interact with the physical world. But in these cases, most of the learning is not happening in the body itself. They are being done offline or happen on some powerful chip. So then the question is, can we embody physical intelligence in a way that can simplify the learning and the control process? Then there is this idea of the rise of embodied artificial intelligence or intelligent matter, where it is defined by different researchers, but I like to take this definition of having sensors that can sense the environment, actuators that can then actuate on the physical world. There needs to be a network connecting these, but there also needs to be some internal memory that is able to coordinate and change the behaviors that this network of actuators and sensors are doing over time. So one way to achieve these type of systems embodied physically is by using mechanical memory and computation. And there has been significant efforts in this regard, but most of those are following binary logic. So they're just trying to translate the type of pervasive logic that is used in computing, and also using the von Neumann computation architecture, where the processors and the memory are not co-located, and there needs to be communication of information between them. So there is here an example of a system that has memory. So it has a memory to kind of capture code, and then it uses mechanical, purely mechanical information processing and communication to understand if the right code is being inputted, then trigger a mechanical wave that changes the system, and in the end, the output of this computation affects the real world by opening the doorknob. So then this type of embodied intelligence, even very simple, has some problems when we try to follow the von Neumann architecture. First one is that one wants to use mechanics to embody a certain level of intelligence. There is a problem with the flow of information. And then the second problem is that once some information has been computed mechanically, there is seldomly the decoding of the information directly affecting the physical world. So there needs to be some layers of systems that are translating these. So then the goal that we are posing is, can we collocate mechanical memory and information processing embodied in a purely mechanical system? So I'm just going to briefly talk about two projects that we are working on embodying closed loop control and embodying collocated memory and computation. So we are leveraging multi-stable structures, and in particular geometrically bistable structures to multi-stable structures to encode different set points into a physical system. So think about, in this case, this little robotic finger is bistable. So upon the action of pressure, the internal structure changes. Due to mechanical constraints, it can keep this shape without the provision of further work. So then if we can build several of these stable states, we can create a sort of final behavior that is dictated by the shape and the geometrical constraints that we have in the system. So this allows us to do sort of embodied open loop control. Now, if we can use, for example, these to actuate soft bodies, in particular soft robots, to go and command to go to specific kinematical shapes. And we can further use the mechanics and the design of the units to not only have a bistable or multi-stable system where the final state needs to be reset or changed by another action, but one can use a concept called metastability. So the units are able to hold their shape for a certain time, but after this time they reset itself, as you're seeing here on the video on the left, and that can be programmed mostly from geometry and from a small degree of the materials that the system are made of. So now we can embody this type of closed-loop control in open loop. Now, can we also embody memory and computation at the same time? So we're playing with a type of system that has very strong hysteresis, that is purely mechanical, and that comes from geometry, not from the material system that the embodiment is made. So in this case, this is a dome pattern sheet that, depending on the order in which it is loaded, you access different shapes. So this is enabling us to program many possible final states depending on the path that the system follows. So if one can see this type of system from the optics of the automata theory. So returning to my previous slide, most work of mechanical intelligence have been focused again on realizing combinatorial logic. So based on logic gates, and there has been beautiful works that have used these very successfully. But we're trying to go a step further and try to find something that has computation and memory happening at the same in the same system, which is, we can refer to it as a finite state machine. So here, it's just one example of a robotic system. In this case, again, half a gripper that has this finite state machine behavior embodied in the geometry. So depending on the order in which the inputs of activating these rows of elements are inputted, one gets a final different behavior. So in this case, we're able to embody a sort of algorithm into the response of the system, that it's purely determined by the geometry of this robot. So with this, I wanted to give you two examples of how can we embody mechanical intelligence going beyond the prevalent use of logic gates and realizing in the embodiment collocated memory and computation, for example, by generating these finite state machines in soft bodies. So this, I thank you for your attention and hope to have a fruitful discussion in the panel session.
Thank you very much, Andreas. Really, really nice and exciting work, and then really well dovetails to the other topics we have. So thank you, Andreas. We'll be coming back to you in the panel discussion at the end. But our next speaker